then I'm still paying you. I got the hard ass beats like the crack of the tech. Still paying you. Think y'all forgot what rap sounded like? I'm still paying you. Back to match up beats, the bang of the average. Still paying you. I'ma make y'all pay for the dues.
DJ isn't here. He's got a long lost brother or something he's got to deal with, who wants his money or whatever, his problem. Sorry, a lot to cover today and next class because we're trying to wrap up the end of the semester. But before we jump into the course material, again, for you guys in the course, Project 4 we do on September 7th. That link there will take you to the recitation from last week with the slides and all that. Homework 6 will go out later today, and that'll be due on the same date on December 7th. And the final exam is December 11th. I'll post on Piazza this week, I'll post the final exam study guide along with the practice exam. Again, please don't make travel plans before this date because we won't be able to reschedule you. And then if you're, as I said last class, we'll be teaching 445, 645 again next semester. If you love the class and can't get enough of it, please sign up to be a TA. If you hate bus tub and think it's the worst code you've ever seen in your life, then also sign up for a TA because we want your opinion on how to fix things. Okay? Any questions about any of these? Yes? The question is how many pages for the cheat sheet for the final exam? It'll be the same as the midterm. The final exam will cover basically from the midterm until next class. Its question is, it's cumulative, not in the sense of like, am I going to ask you like specific questions like buffer pool stuff that we covered during the midterm, but like you got to know what SQL is, you got to know what relational algebra is because you like that's the background you need to understand all these other things. But the emphasis will be on things that came after the midterm. Other questions? And then it's a 3-hour. The slot is 3 hours, but it'll be the same. It'd be roughly the same length as it would have been on the midterm, so that you can complete it in 1 hour and 20 minutes. But if you want to take the full 3 hours, go for it. Okay? All right, database talks we have coming up. Today, after class, we have a guy in the UK building a system called XTDB. This is a time series database system. We haven't really talked about time series too much, but it's basically, think of like you keeping track of time as a first class concept on tuples inside your database system. And I think what's cool that they can do is they can do multi-dimensional time. So he'll cover that. Then a week from now, we'll have the guys from Snowflake building this thing called Apache Polaris. It's the catalog. It's a open source re-implementation of the Apache Iceberg catalog. Again, the background was Snowflake tried to buy Iceberg for $600 million. Databricks caught wind of that and came in and blew them out and paying for $1 billion for the Iceberg team. It was a company that had 40 people, had some revenue, but not $1 billion worth of revenue. And they got bought by Databricks. And then so Snowflake made their own open source version called Polaris. But again, it's not to say that Snowflake is incompatible with Iceberg. It's just they weren't able to buy the Iceberg people. And then we've had an addendum to the schedule for the seminar series this semester. There's an Apache project called Floose. I actually don't know what this does, but they sent me a lot of emails begging to give a talk. So we'll figure out what they're going to do. I've never heard of it prior to them reaching out to me, and then I've never run across anybody using it. Okay. All right. And that'll be the Floose talk will be the last talk for the semester, and then we'll kick off the seminar series in the spring. Again, even if you graduate and leave, or leaving CMU, if you still want to be involved and watch these videos on Zoom, please join us. A lot of my former students show up on these things. All right, so here's where we're at for this semester. All right, what we've accomplished so far. As I said at the end of last class, we now know how to build a single node database system. Right? You know how to make it transactional, how to make it fault tolerant. We know how to run queries on it, do some query planning for the SQL queries that show up. And so now this class and next class is to now discuss at a high level what distributed database systems look like. And again, the databases themselves are hard to understand and build correctly. And distributed databases just make this all even harder. That's why we do single node stuff first, get the fundamentals down, and then we can understand how to make things distributed. Right? And it's the same architecture we've been talking about. It's just now it's split across 2 or more nodes. And the questions we're going to talk about today and next class is how we're actually going to be communicating across these nodes, whether we're going from the top down or we're coming from the bottom up, or actually something more in the middle, where we're coordinating across like the buffer pools, for example, right? So all the things that we talked about for the entire semester, like how to run queries fast, how to make sure that if you crash and come back, you don't lose any data, all that is still applicable here. It's just now we're talking about how to do this across multiple machines, okay? Then also recall we had the discussion when we talked about parallel query execution on a single node. We made the distinction between parallel database systems and distributed database systems, right? And I said in a parallel database system, think of that like a single machine, could have multiple cores or multiple CPU sockets, and the communication between these different workers in our database would be very fast and assumed to be reliable, right? Like we can send messages over an IPC from one process or one thread to the next, and it's guaranteed to show up, right? If it doesn't show up, then our CPU is melting down. We have other problems. So now for distributed data systems, now we can't ignore some of the things we could ignore in parallel databases. For example, we can't assume that communicating between the nodes is going to be fast, right? Because I might have to go around the other side of the planet, and now you're limited by the speed of light, and that can take 100, 300 milliseconds. Worst case scenario, up in the tens of seconds or even minutes if things get lost and things recover in weird ways. And so not only is communication between the workers going to be much slower, orders of magnitude slower, it's also potentially unreliable, meaning we could send a message from one node to the next, and that message may not show up because the network got severed, the packet got dropped, whatever, right? Or in some cases, and this is sometimes common too, is that I send my message to the other worker or to the other node, and it's running, Go or Java, pick your favorite memory managed environment, and then the garbage collector kicks in. Like in the JVM, if you have a huge heap, the JVM can block, the garbage collection can block all execution for 10, 30 seconds, worst case scenario. So now it looks like that node doesn't exist anymore, but it's just waiting to clean some stuff up before it can process your message. So now how do you actually want to handle that? So if you take a distributed systems course, they talk a lot about consensus protocols, right? Paxos, RAF, things like that. All of that is going to be applicable here. We'll build up to that. We first want to understand what the architecture of our data system is going to look like. And then we'll apply these different techniques to layer on top of them and make these things more reliable and fault tolerant. Right, so this is what I've already said before, right? Just because we're going multi-node doesn't mean we can throw away the entire textbook or everything we talked about this entire semester. All the things we talked about so far matter in this world as well. It's just everything's more complicated now because we're dealing with multiple hardware, multiple machines, potentially running in different data centers, and in some cases with disparate hardware resources. Like my node over in that other data center there might have fewer cores than I do. So now I got to consider that in how I do my query optimization, my planning, how I'm going to maybe run my concurrency protocol, what transaction should run where. All that we have to deal with. So there's some high-level design decisions we're going to cover for the next 2 lectures of how to build a distributed data system. The first is going to be how does an application find the data, right? If now my database can be split across multiple nodes or managed by multiple nodes, who does the application actually talk to, right? It was simple when it was one node. I just connect to it through whatever the communication protocol, the network protocol that the data system exposed to me. I know my data is going to be there. But now if my data is split across multiple machines, how do I go and find it? And where do I send the actual queries to it? Then we're talking about how we want to divide the resources of the database system across these different workers or nodes, right? Do we split things up on a per table basis, or we do something more fine-grained? And then how does the application know that I split things up a certain way, if at all, to go find the data that needs to run a query? And then when a query shows up on one of these workers in our distributed system, how are they going to execute that query? And especially if the data that the query needs to access isn't on the machine that my query is actually running. Do I send the query to where the data is located, or do I pull the data to where I'm located, my query is executing, and run things there? And then, of course, again, as I sort of said, in the world of distributed systems, this matters a lot. And the distributed system is basically a database system. That's at the end of the day. So how to make sure that we guarantee consistency and correctness across our entire database system, so that the application doesn't deal with any of the anomalies and issues that we've talked about before. And in some systems, they're just going to throw caution to the wind and say, well, guaranteeing consistency and correctness is hard, so we're not going to really do it. We're not going to do it immediately. And then, what are the implications of that in your application? Okay. So for today's lecture, it's going to be sort of a hodgepodge of ideas of building up the basics of what a distributed database system is going to look like for us. And then next class, we'll go in more detail of how we're going to do distributed currency control and how we're going to run distributed OLAP queries, so distributed analytical queries. Or how do we do joins across multiple nodes, for example. Okay? So first talk about what the high-level system architectures could look like. Then we'll talk about how to split up the data in our partitioning schemes. Then we'll talk about replication, how to make sure that if we have multiple copies of data, we need for fault tolerance, how to make sure that those are going to be in sync, and then we'll segue into how to do transactions across these things, right? Again, another key difference about distributed databases and parallel databases is that parallel databases, you're adding more resources to get better performance. In a distributed database system, we want to do that as well. We want to add more resources to get better performance, but sometimes we also want to add more resources so we get better fault tolerance or availability. So if one node goes down, right, the application can still keep running and query the database. Right? Again, if it's a parallel database running on a single box, it's kind of hard to do. All right, so the first thing we're going to discuss is what the system architecture is going to look like. And this is going to specify, or this is going to determine how the resources that are available to us on a machine, on a computing machine, how they're going to be accessed and maintained by the database system, and then how these resources are going to communicate with each other, right? And you can sort of think of like the CPU is obviously the central processing unit, but it's the computational unit on a single node in our system, but it has to have memory, it has to have disk. The question is, where is the disk and where's the memory amongst other nodes in the system? So this terminology goes back to the 1980s. It's the definition of these categories of what these databases look like. So without you knowing it, everything we've talked about this semester so far is called a shared everything system. And the idea is that on a single node, it has the CPU, and the CPU can talk to its own memory and can talk to its own disk. Right? Everything is encapsulated on a single box. A shared nothing system is where there is individual nodes that each have their own CPU, their own local memory, and their own local disk. And the only way they can communicate with other nodes in our distributed system is through some high-level network up above. So basically, the CPU on one node can't read into the memory or disk of another node directly. It has to send a message that the CPU then processes on the other node and say, hey, I want this block of data, or I want you to do this for me, and gets back the result. And this network most often is going to be TCP/IP. There are some systems where they can do UDP. Some systems can do more fancy things with like Mellon, RDMA. But in general, assume that we're just opening up TCP sockets and sending messages back and forth. Another architecture is called shared disk. And this is where every node is going to have its own CPU and own memory. But the database, the primary resting location of the database, is now going to be on some global disk that all the nodes can read and write to. Right? So now if I want to send a message to another node, you still would do TCP up above, but if I want to read data, I could, on another node, I don't have to go over TCP/IP to communicate with the other nodes. I go directly down to the disk and go and get it. And then this one is theoretical. It's in the academic literature, but I'm not aware of any data system that actually does this outside of like the high performance computing world, like scientific stuff. It's called shared memory. Basically, every node only has a stateless CPU, and then the memory and the disk is shared across all the different nodes. This question is, isn't a shared everything system fundamentally a shared memory system? So you're trying to say, yeah. So now just think about having multiple nodes, right? If I have multiple of these shared everything, then I'm essentially shared nothing, because again, the CPU can't read and write to the disk or memory on the other nodes without going through the network at the top. The question is, shared everything fundamentally a single machine? Yes. The question is, are we treating shared disks as having multiple disks? Meaning like I'm showing one, but it can have more? Yeah. We'll get there, yes. But it looks logically as one disk that everyone can read and write to. S3, yes, they're correct. We're getting there. S3 would be shared disk. The question is for share nothing, is the network what, sorry? For ingress? For data coming in? Well, no. So like if a query, we haven't talked about like what we're communicating with. Say a query shows up on one of these nodes, right? This middle node here, and that query needs to read data on this other node. Can't go reach into that other node and into a disk directly or its memory and go read stuff. It's got to send a message that the CPU then processes and says, "Oh, they want this data. Let me send it back over to you." So shared everything is most common because most people build a single node database system first. Right? For shared nothing, this was the way you would build a distributed database going back to the 1980s. Like the guy that invented Postgres, Mike Snowbreaker, wrote a paper in '86, sort of touting the advantages of shared nothing systems. And this is how people build basically shared nothing systems for 20, 30 years. The popularity is on the decline now because of the cloud, things like S3 and other distributed architectures. Like most of the newer systems today are going to be shared disk. Yes. Question is Spanner shared nothing or shared disk? Spanner is shared nothing. But it reads and writes from Borg, like the distributed file system. So like the lines get blurred, right? All right, this last one here, so again, as far as I know, nobody does this, so we're not spending any time on it. All right, so shared nothing. Shared nothing, again, is every single node has its own local disk and own local memory. And then anytime you need to communicate with another node, you got to send a message over that network. So again, you can't just go reach down into the other node and get the data you want, right? So this is going to get the best performance you can have in a distributed database system because every node can process the data that it just has, and it's going to be the most efficient way to access things, right? Because I don't have to go reach in other nodes, go get the data that I need, and go process everything I need locally. Right? The challenge is going to be, and this is why in the cloud world, the shared disk is more popular, is that this can be harder to scale out. If I want to add new nodes, I can't just say, you have new nodes, now point to the same shared disk. I actually get to physically move data. And we'll see an example in a second. All right, next slide. Right, so that's why, again, this is going to get the best performance, but if I have to start adding and dropping nodes, right, either because I want to scale up and add more machines, or scale out and add more machines, or because the node goes down and I got to recover from it, then this is probably problematic. So again, there's a lot of systems in this space. I can't say anyone is more popular than others, but like this is basically how people build. People say they have a distributed database system from the 80s or 90s or mid 2000s. It's going to be shared nothing. All right, so here's what it looks like. So you have the application server, and then it can communicate to some kind of catalog metadata thing. Right? And again, this could be just another node in a system, could be a centralized node. We'll get to that architecture in a second. But the case, this is going to say, here's how to go find the data you're looking for. And then say we want to run a query, get ID equals 200. So each node would have, again, a partition, or it's a disjoint subset of the total table, or the total amount of data in our database. For now, assuming we only have one table, and it has IDs from 1 to 300. So if I want to, again, I know I want to get access ID equals 200. I know this node is maintaining this data, so I send my query to that node, and it can process it and return the result. No problem there, right? But then the challenge is going to be if I want to start doing things like I want to get ID equals 100 and ID equals 200 in the same query, and I send the query to the first node here. The different nodes are aware of the topology of the database, of the partitioning scheme that's defined in the catalog. Again, we'll cover that in a second. So it knows that the top node doesn't have ID equals 200, so it has to send a message down here to say, I need ID equals 200. And it could either tell the node down below, run this query or this portion of the query, give me ID 200 and give me back the result, or it could actually just send the actual data itself up and then let the node on the top process the data, right? Now, the challenge I was saying is that this is going to get great performance if all your queries are only accessing data that's on each individual node. But when I want to scale out, meaning I want to add a new machine, then the problem is that now I have to move data around. So if I add a new node in the middle here, I got to now take half the data that I had in the node at the bottom, half of the data that I had a node at the top, and copy that into the middle one here. And then you update the catalog service and say, here's the data's moved around, so anybody comes looking for that data will find it. Yes? So the question is, would the application server know the data ranges? Ideally, no. Some systems, yes, but ideally, no. Again, if you think about in SQL, the same query that I could write on a database that runs on a single box, that same query should still work in a distributed database system. Like should have completely transparent to me how the data is moving around, right? So my example at the beginning, it connected to the application server. Some systems will do that. You can go to the application server and say, where's my data going to be? And other systems, you could just send it to any one of these nodes, and they know where the data is because it's in the catalog. And the catalog is just another database. We haven't really talked about catalogs too much, but like you have your data, like the user data, the application data, and then you have this metadata catalog that keeps track of like, here's the tables I have, here's the schemas that they have, the columns I have, the constraints. Well, now you can also start putting things like, here's the partitioning schema, here's my layout of my data, my topology of my network. And then you want the same sort of transactional guarantees you want for regular application data, you want that to be in your catalog data too. The question is how should I maintain indexes in this, right? So in some cases, like where ID equals this range here, each node in this environment would have an index just for the data that they have. And again, if all my queries are like get ID equals 200, get equals 100, I can look at the SQL query, figure out what data it actually needs, send the data to that node, and that node can then do its own lookup in its own slice of the index, right? So each node has a portion of the total index. There's also the case where you may have secondary indexes, where you may have things that don't align up with how you're splitting up the data, and that you got to put either on a one node that everyone goes to and talks to, or you replicate it across all nodes.
What if you do some kind of an insert and then everything needs to be moved around? So do you move stuff across different nodes as well? For example, BT that's transit across multiple.
The question is, if I insert something and it has to.
For example, we insert one to the other, fill up the entire space, we insert a new value that like overruns the entire space, so you can move one of the values to the other node.
Because like this node gets full. Yeah. We'll cover that in a second. This is how we handle partitioning. We'll talk about that in a second. Depending on the partitioning scheme, depending on your criteria, whether when you actually want to move data, you make that decision when you want to do that. And then depending on the partitioning scheme, like consistent hashing and rendezvous hashing, like some nodes make it, some schemes make it very easy to move data around. This is just like a toy example. I'm doing range partitioning here. But I would say what you're talking about is actually what MongoDB did in the early days. Sort of what part of the reason MongoDB got popular in like early 2010s was they had this capability of auto sharding. So they had the ability to do exactly as you were saying, like, oh, my shard gets too full, or all the queries are going here. They could split off a chunk of it and rebalance things automatically. But it was a total hack because they didn't guarantee that the catalog was in sync with the data that got moved. So you may have two copies of the data on two nodes or two partitions, and two different queries might update the same thing and get incorrect results. Like, or they took a lock entire database and then move things around. That's another way to handle it. Yes?
So for this simple example here, why doesn't the node directly send the ID equals 200 back to the application server instead of taking a detour?
The question is, so for this query here, ID equals 100 and ID equals 200. Say it's one query, right? Select star from where ID in 100, 200. So your question is, why didn't the node at the top send the query down here, or what? Sorry.
I directly send the ID equals 200. So 200 itself directly back to the application server.
Oh, the question is, why didn't the good point. Why didn't this node here send the ID equals 200 sub-result back to the application server? Because like the thing of how the application server communicates with the data server, it sends, say this is one query, right? Select star, not two gets, right? They send one select query to one node, and then the call and response protocol of JDBC or ODBC is that I'm going to get one result back with all the tuples that I want for my query. The applications aren't written such that you can send one query and now get two things back, right? It's just not how people write these code. And in the same way that like, and you can imagine you could change the API to do that, but like on the client drivers to support this, but like it's the thing I was saying before. Like this, if I write the same query and runs on a single node, I should get back roughly approximately the same result I would if it's even across multiple nodes. The database itself should be treated as, yeah, like that's the point of SQL. SQL, you don't know how the data is being split up. So my SQL query gets sent to the server, and the server then decides how to farm it out across the different nodes. And then the application should know, shouldn't care.
The second question is, so to some extent, so all the nodes here are actually non-homogeneous. So for a specific node, it's treated as a master node.
The question is, should I think of these nodes as being all homogeneous, or would there be a master or primary node? Yeah. Not yet. For this example, the key thing about these examples, I'm trying to show that like every node has a slice of the database, and the other node at the top can't just go down and go look at it. It has to send messages. Let me keep going, and then it'll come up. All right. All right. So again, if I add a new node, I got to move things around. All right. So shared disk, and the idea here is that every node in my system is going to have its own local CPU, own local memory. They are going to have local disk too, like directly attached storage, like an SSD. But that's only really used for caching. Like if my memory gets full, I want to spill to that. But the primary storage location of the database is going to be down on this shared disk infrastructure down below. And as they pointed out, oh, is this S3? Yes, this is going to be like some distributed file system or kind of distributed object store, like Amazon S3 or Azure Blob Store, or their GCS Cloud Compute Storage, right? For Google, right? The basic idea is that it's this single logical device where all the nodes can read and write to, right? And that's considered the primary resting database, the resting location of the database, right? So when people talk about data lakes or serverless systems, right, it looks a lot like this. And again, most of the newer database systems, distributed database systems built in the last 10 years, especially for analytical workloads, like the Snowflakes, the Databricks, the Fireballs, Yellowbricks, and all those guys, all of them are going to look a lot like this, right? So now the architecture is basically the same as before, but now we have this shared storage thing on the back, and query shows up. In this case here, we're ignoring the fact, how do we find where the node I want to communicate with is, right? Assuming it's been told through the catalog service or some front end. And now this query wants to get ID equal 101. It goes to the catalog and it says, who's responsible for this? Where do I go find this data? And now I can make a request for a page or a block or a file, whatever from the distributed file system. And it goes, then makes a copy of that and brings it back into its memory. So same here, I get 102. I know it's on page XYZ. So I go to my storage device and go and get it, right? And then now, again, when I add a new node in my distributed system, unlike before in shared nothing where I had to copy data around, now I only have to do a logical assignment in the catalog to say this new node is now responsible for data found within some range or some partition. So I don't want to move any data when I add this new node. It's just now all the other nodes need to be aware that this node in the middle now is responsible for key 101, whereas before the one at the top was. Yes? Question is, do we need to have different nodes be responsible for different ranges? Can't just be any node can handle any possible data. We'll get in a second. If you start doing updates to that data, how do you know if I update, how do I know if I update on this node here, who has a copy of that data and make sure that they see it? Because again, when it was all in a single box, if I update something, it's like the global data that everyone sees. But if this bottom guy here updates key 102, but then the nodes at the top have a copy of key 102 as well, how do I make sure that they get notified that they have the latest version? What's that? Locking on what? Yes? 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 Where's the lock? Everywhere? So that means that, like, if I want to lock one thing, I got to broadcast to everyone I hold the lock for it? Is that not a good idea? Okay, can it be a primary node or master node? Yes, we'll get there in a second. Yes. Well, this is the exact thing I was just saying. So say I now update page 101, right? I then write to the page here, but now I got to notify potentially everyone else to say, if you have a copy of page ABC, I've updated 101 in this way, right? And so that anytime that they go read this data, they would know that they have to go fetch the latest version, either from the node that's responsible for it or from the shared disk. Again, we'll cover how we do it in a second. The other great thing about shared disk architectures too, and again, this is why they're so prominent now in the cloud, is that this storage is basically infinite. Meaning if I want to add additional capacity, that's trivial to do in S3 because I give Amazon more money and I get more space. Like your credit card will run out of money before Amazon runs out of storage space for you, right? And then if I add more capacity, I don't have to move things around or even take nodes offline in the same way that I would have in a shared nothing system. If I want to add new disks to shared nothing, I got to go physically add that into the box itself.
What makes the performance worse compared to the other cases? Is it because of just the network overhead of having a different storage tier?
The question is, why is the performance in a shared disk architecture worse than a shared nothing architecture? Because I got to communicate with some other device to get the data that I need. And for OLTP, the way you get around that, you just have every node cache it, right? But then you still have to care about, like, if I update things, like I have to still make it back out here. Question is, is the slowdown due to the overhead of the network I/O for updating disk? Yes. Also, again, if I have a transaction, we're not there yet. If I have a transaction that touches multiple nodes, and I go say commit, I got to get everyone to agree that now it's okay to commit this. So now I'm sending you a message. I got to wait for you to come back and acknowledge that you got my commit message. Like that becomes problematic as well. But that's going to happen in shared nothing or shared disk as well, right? In shared disk specifically, it's going to have the overhead of communicating to disk somewhere else. All right. So we sort of been talking about this concept as well, with like how we're actually now going to execute queries, either whether it's shared disk or shared nothing, right? And it has to do with when a query shows up and on a node, and I recognize that the data I need on that node for this particular query isn't local to me, either because it's not in my local cache, or it's not on my local disk because I'm responsible for it. It's on some other node or the shared disk architecture, right? Some remote storage device. How do I decide whether I want to pull the data to me and so I can run my query, or do I push my query or the portion of the query I want to execute to where the data is actually residing? So the two approaches, again, push versus pull. So pushing the query to the data means that I can carve off either take the entire query or a portion of the query and send it to whatever the data is being located. And assuming I have compute capacity or some computing resource, like something that can execute things on where the data is being located, I can then run the portion of the query that I need on that remote storage, and then have it send back to me the result of that computation. Pulling the data of the query means that the data is at some other location. I'm basically going to copy the bytes out directly to where my node is over the network, so that then I can run it as if I had the data local to me already. Again, these are not mutually exclusive. And the lines get blurry because in some of these systems, the storage layer can actually do some computation. So just taking S3, for example, S3, although it's not deprecated, but if you sign up for a new account today, you can't get this. But if you have an existing account with AWS as of last year, you can get this. But they have a feature called S3 Select, where you can send a request to S3 and say, go get this data for me. But then you also tag along a SQL query that then does some processing on the node where the data is actually being stored, and then they send back to you the subset of the result. So you can use it for filtering. You obviously can't do joins or more complex computation, but you can push down predicates to S3 so that now you pay less egress costs, the network transfer costs going from S3 to your storage device. Yes? The question is, why do they deprecate it? I don't know. Do I think it's a bad? the question is, do I think it's a bad idea? Do I think it's a bad business idea, or do I think it's a bad database idea? I think it's a bad database idea because this is super useful. But I don't know if any systems actually use it. But it makes sense, right? If I have I have 1 petabyte of data on S3, and I don't want to have to transfer all that to me, if I can do some push down some predicates. Now again, you can't, how do you say this? The question is, the issue is now that a core component of your database is now outside your control. Yes. But like, how does this? And I know I made a big deal about saying like, don't trust the OS is going to ruin our lives. And now I'm saying go trust Amazon to do something, right? So it depends on what you're trying to do. For some things, yes. For some things, no. This might be a good idea, right? For simple things, maybe it's okay. But like, and assuming you can parallelize it enough, like assuming you can have enough concurrent requests to different S3 buckets, and they can all do the processing in parallel, right? So now I can take my single box that has maybe like 20 cores, but if I have 1,000 outstanding requests S3, I don't think they let you do that. But like I could have all of them run as if there was 1,000 cores doing filtering at the same time. Now you pay for that, right? And it might be cheaper to do the processing yourself, but then you got to account for like the cost of moving the petabyte of data out of S3 to you. But then you can cache that in the local SSD, but now you got to pay for that to caching. You know what I mean? There's trade-offs to all these things. It's a one-time cost. Assuming that you doesn't get evicted because you brought something else in, right? All the bufferable stuff we talked about before still matters. Yes?
Even without that, is there a way to like do it yourself by like having some logic that only those chunks of S3 objects?
The question is, without doing this S3 select, is there a way to achieve this on the data server side where you don't have to maybe pull the entire buckets in? Yes. So it's all the same stuff we talked about before. Like just because it's running on S3 doesn't change like that we care about indexes, we care about filters, the zone map stuff. Like if I have enough metadata up in my database system about what's in my S3 buckets, I can make more precise decisions on what data I'm actually feeding in. Absolutely, yes. But like someone has to write that logic, and that'll be in the data server, and assumes that you even have that metadata to begin with. If someone's putting down Parquet files and buckets you've never seen before, you don't have any metadata until you go actually read it. But then you go read the footer, and that'll give you the metadata that way. So then you read less and decide whether you need to read the rest of the file. What's that? You got to read the footer and bring it into the data server side. But that footer is going to be, I don't know, a megabyte if that. But again, all the same stuff we talked about before. Like I want to do predicate push down, projection push down. I want to use zone maps and other filters aside. What's the bare minimum data I need to read? Just because it's S3 versus a local DIX in the same box, that all the same principles apply. Now it's just harder. Right, so in the case of Microsoft, they have not as sophisticated as S3, but it's basically the same idea, right? All right, so pushing query the data, the idea here is that if I say I know that I want to run this query here, and the data I need for that query is down below, rather than moving all the data up to compute this join up into the node at the top, I'll send down a plan fragment and say, hey, I want to do this join in RNS. I know you have the data in the range between 101 and 200. Compute the local join in this node down here, and then send me up now the result of the join, or at least the partial result of the join, and then I can combine together the result in the node at the top. Now again, I'm showing this in a shared nothing architecture, but the same concept applies in a shared disk architecture. It's just more readily apparent that you could do it this way. In a shared disk system, the idea is that the nodes are responsible for managing some logical portion of the data, right? But the final physical resting place of that data is going to be out on the disk. So in this case here, assuming there's nothing in our local caches, this query shows up, and I want to do the same join I was doing before. But the node at the top will say, I know the node at the bottom is responsible for data within this range. So rather than me pulling from the shared disk, computing the join at the top, I'm going to send my plan fragment down to the bottom guy, tell them to compute the partial result for the join. It knows how to go out to the shared disk, the shared storage, and get all the data it needs, bring that copy back into its local cache. Then the bottom guy here computes the portion of the join that it's responsible for, sends the result up to the node at the top, and the node at the top then can either union the results together and produce the final result, or if there's additional things it wants to do as part of the query, it knows how to then further process them as needed. So again, another key distinction here in a shared disk versus the shared nothing architecture. In a shared disk architecture, I'm showing the same partitioning ranges that we had in shared nothing, but again, this is a logical partitioning. So the final resting, the data is going to always be on shared disk. We're saying that for this point in time, this node at the bottom is responsible for the data within this range. So if an update comes along, we know that it has to go to this node here, because that'll be, again, the primary or the master, or whatever you want to call it. That's where the change has to be applied first. And then this node is responsible for them making sure that things get propagated to the other nodes in the cluster or the system. Yes?
You always partition those by data into partition by which servers are using it.
Boom, next slide. Okay. How are we deciding to partition things, right? So again, we want to split the database across multiple resources, either disk or nodes or processes, right? In my examples here, I'm showing we're partitioning on keys within the table, right? Like this is sort of fine-grained partitioning. We're trying to say, I'm going to pick one or more columns in my tables, and that's going to be the partitioning key, and I'll use whatever the partitioning mechanism I'm going to have to then decide what partition is going to get assigned to. It doesn't have to be that fine-grained. It can be more coarse-grained. Like in Yellowbrick and Snowflake, they partition on files. A bunch of Parquet files sitting in S3, and they're going to say which node is going to be responsible for them, right? And the idea is that if I partition my database across these different disjoint subsets, or they're not always disjoint, they usually are, then again, I just write my query against that data. There's something that's coordinating, figuring out where the data is all being located. It knows how to send the plan fragments to those nodes that are responsible for those partitions to compute some portion of the query, and then I know how to combine the results back together to produce the final result. And in the case of shared nothing, it's going to be physically partitioned. Like the data itself, the final resting place or the primary storage location of the data is going to be within the partition running on a single node. Or in the case of shared disk, it's logical partitioning in that we're saying that there's some node in our system is responsible for that partition of the data, but the final resting place has to be back on shared disk. You sort of think of like in a shared disk architecture, the nodes themselves are stateless, meaning if one of those guys gets killed and crashes, come back and crashes, I don't lose any data because the shared disk is the final resting place for it, and I know that's always going to be there, as long as my credit card still works with Amazon. Yes?
So the entire semester we talked about database files with a very specific layout, like built for the DNS. And now that we're talking about shared disk, you keep mentioning Parquet. So like, what changed? Like, why use Parquet?
All right. So the question is, during the entire semester, I keep saying, oh, we're going to have here's the file layout, and within that, there's pages, and the pages have these slotted page architecture, right, or the LSM stuff. And now I keep mentioning Parquet. Why do I mention that in the context of distributed databases? So Parquet files are just a open source columnar file format that are very common in distributed shared disk OLAP systems, right? And what Parquet allows you to do is like you can have one application create a bunch of data and just write it to S3 without going through the database server, and then the database server then can run queries on it, right? So it's just a file format, and it's very common to use this in a shared disk cloud system, like Lakehouse system. Doesn't have to be, and everything I'm saying so far is I'm not defining what's actually in the data I'm storing in the shared disk or even in the shared nothing system. I'm just mentioning Parquet is an example of what people do in the cloud systems, but it's still going to be, at the high level, it's still going to be all the stuff we talked about the entire semester. Like it's going to be a PAX layout or going to be slotted pages or LSM, right?
But isn't it true that like your data will always come from another application? Like why suddenly do we want to like take the
So the question is why? Statement is, it's not true that like the files are always going to come from an outside application. Yes, most of the data will come through into the database server as inserts, especially in OLTP. We're just going to write that in. That doesn't change.
I'm just surprised that we're suddenly okay with using like some random old standard open source file format.
Parquet?
Yeah.
I wouldn't say Parquet is random. It's used everywhere.
Yeah, I
And
get back to Rendezvous.
and old, I mean, it's, I mean,
No, but isn't it true that our own file format that we design for our DMS will always be better and more efficient?
the question, wait, the file format for like in this class? But
Yeah.
the question is it?
Well, I mean, in general, like the file format that you build for your DMS.
Yeah. So his statement is it not true that a customized file format would be better than a general purpose open source file format? It depends on I mean, it's a cop out. Depends on the workload, depends on the data, depends on where the environment that you're actually running your data system, right? So what's that? Yeah, so we'll get to the end, but there's a philosophical discussion to be had about where to spend your energy when you're building a new database system. So Snowflake famously decided, we're not going to go shared nothing. We're going to be shared disk. I'll get to your answer about the file formats in a second. But Snowflake said, we don't want to be shared nothing, because if I'm shared nothing, then I got to build basically a distributed. I got to make sure that like my storage is fault tolerant and sync and keep these things synchronized and things like that. And they decided they're not going to do that. They said we're going to build everything off of S3 and just put caching in front of that on these stateless nodes so that we can run hide the latency cost of doing this. And then the thought was, let's spend all our energy, Snowflake's energy, on engineering time on making this thing as fast as possible, and then we'll put caching in front of that to hide this latency. And then as Amazon makes this better, we'll get that benefit for free. So that was one of the smart things that they did in the early days. Now again, that kind of goes against what I said before. We're like, we want to control everything, but for distributed OLAP, it's kind of it's okay to do that, because again, if I'm a startup, it's one less thing I have to build. Amazon's gonna put a bunch of engineers making this work really great. For OLTP, maybe less so, because I really care about like performance latency stuff. All right, so now your question about the file format thing, right? So if I could, how to say this? Database systems are usually trying to be this general purpose software that can accommodate as many application scenarios as possible, and hardware discrepancies in different hardware characteristics in different operating environments, right? So it is true that if I have an application that I could build a database server that could serve one application, I can build a optimized, customized version of everything we talked about the entire semester and make that one application run as fast as possible. Absolutely, yes, you could do that. If you're trying to make it general purpose, though, that's actually not feasible. So now you got to make decisions of what's the lowest common denominator I would need to be able to support a large number of applications so that I can sell my database system and then not have huge performance bottlenecks. So you said Parquet is old. Parquet came out in 2013, right? So it's 12 years old now. At the time, that was considered a state-of-the-art file format because everyone was storing things in JSON or CSVs, right? So you're beating those. But then now, are there better compression protocols and more advanced ways of accessing columnar data? Yes, and Parquet has not really kept up with that. And that's why there's like Vortex and all these other file formats that are coming along. But again, I'm only bringing that up to say in the cloud, in distributed database systems, for analytical workloads, oftentimes what's going to be in the storage layer is going to be a bunch of Parquet files. And can you build better ones? Yes, and the Spiral guys and others are trying to do that. Okay. All right, so partitioning. All right, so one basic way to do partitioning is to do table partitioning, meaning like I'll have one node be responsible for one table and another node be responsible for another table. And I literally split up that coarse grain. And you can need more coarse grain, like I have one node be responsible for a database, this database, and one node responsible for that database. And of course, if now I need to access data across multiple tables and across multiple databases, if I'm doing this naive scheme, it becomes problematic. But in some scenarios, this works out just fine. So again, say my database has two tables, 1 and 2. And I'm literally going to take all the data from the first table, put it in one node here, all the data in the second table, put it in another node here. As long as my queries only access data in one table, then I'm happy, I'm great. Right? Of course, now if my table doesn't fit on a single partition, then this becomes problematic, and I got to do something else. So I've come across this actually with people using Mongo, where they had the regular database, or most of the application data was partitioned in the way we'll talk about next slide. But then they had one table was basically a log for the application. And they only inserted into it, and they never read it. So they wanted to put that table or collection in Mongo parlance on a single partition or single node by itself, because this just inserted and make that run as fast as possible, and it didn't interfere with any other updates on any other nodes. So this is not that common, but some systems that do let you do this. And in some cases, we'll see this when we talk about OLAP queries next class. Instead of just putting, you put the entire table at a node, but you'll make a replica of it on every node, because it's like something really small, like a zip code table. There's only like 35,000 records. That's not that big. And I'll make a copy of that on every single node. So anytime a query wants to run, it always can be the local copy of that table. The question is, doesn't that introduce also the cost of updates every time? Yeah, but like for some cases, those tables aren't updated that often. The postal service updates the zip code table 4 times a year, right? Like, not that often. All right, so what is most common and what people normally think about in distributed databases is doing what's called horizontal partitioning. And in the NoSQL guys, they'll call this sharding. It's basically the same thing. And then we're going to split we'll show an example of doing sort of fine-grained horizontal partitioning, where within one table, we're going to look at some partitioning column or columns, and we're going to use that to decide how we're going to split things up. And the goal here is we want to split the data up in according to a bunch of objectives, like make sure every node has the same amount of data, make sure that every node is going to run the same amount of queries, right? You may have one node have a small amount of data, but it gets all the queries, and so therefore you don't want to put more data on it, because that'll slow down, that'll sort of overwhelm it. So the 2 most common schemes to do horizontal partitioning is to do hash partitioning and range partitioning. Range partitioning we've already seen, right? I just took like discrete subsets of values that are continuous ranges within my key space of a column, and I'm just assigning those to different nodes. And how you come up with the optimal ranges, depends on what you're trying to, what your objective function is. Predicate partitioning, horizontal partitioning is not that common. The basic idea is that you just define where clauses to say, where name equals Andy and age equals 1, 2, 3, that goes to this node. And then where name equals Andy and age equals 4, 5, 6, that goes to another node, right? Basically defining the where clauses, how to split data up. And then round robin partitioning is just assigning some tuples or files or data to one node in a round robin fashion. Like I said, hashing and range partition is more common. So say this is our table. Again, we have 4 columns here, and we're going to pick one of them as the partitioning key, right? It could be multiple ones. Usually it's the primary key, but it doesn't always have to be, right? And then now, if we're doing hash partitioning, what we're going to do is for every single tuple, we're going to take whatever the value is for that partitioning column, partitioning key, and we're going to hash it, mod by the number of partitions we have in our system, in this case 4, and then that's going to determine how we're going to assign the data from these different tuples to these different partitions, right? And if most of my queries, or if my queries just have the partition key in the where clause, then this is going to be fantastic for me, because I can just look at the catalog and say, well, I know the value being used for the partition key. Look at my where clause. I hash it in the same way I did for when I moved the data in the beginning, and that's going to tell me which node has the data that I'm looking for. So for shared disk, right? Basic idea looks like this, right? I want to get ID equals 1, assuming I've done some amount of partitioning, and it knows that it can get data from the different nodes that it needs. Right? In this case here, if I had to get multiple keys and one of those keys aren't in my node that I need, then I know I need to go communicate with the guy at the top, either to send the query that I want it to run for me, or pull the data down that I need to then run things locally. And again, this is logical partitioning, because again, the final resting place of the data is out here on the shared disk. Shared nothing, again, the final resting place of the data is actually on the nodes themselves. So depending on the queries I'm executing, I know how to route the things that go get the data that I need. We've already covered this. All right, in the case of hash partitioning, what's one key problem with this approach? All right, so the question is, any other query that doesn't have the partition key has to get broadcast to everyone? Yes. Or even if I have the partitioning key, but I do a range query, then that's going to break me as well, because like now, if it's between partition key between 1 and 1,000, I may not have a continuous range, but then again, so I don't know what the data is actually going to be located. I'm just hashing things. So this doesn't work, again, if it's very fine grained and you're doing things that aren't exactly the quality predicate I need for my lookup. What's another problem with this?
Maybe change the number of partitions.
Boom. Another partition shows up, another node shows up, or one of these partitions dies, right? And then now, before, when I was taking the hash and modding my 4, now I got to go through and mod by 5. And now the location of the data may change because what partition gets mapped to has changed, right? So again, range partitioning is going to have the same problem, because if I add a new node, then I have to start shuffling ranges around, and it may not be isolated to just moving data from a single partition. Yes. Can you use stable partitioning? Next slide. All right, so there's 2 ways to get around this problem. And the first would be consistent hashing, which was the hot thing 10 years ago or so. And then the next one would be rendezvous hashing. And consistent hashing is a subset of rendezvous hashing, but consistent hashing it's neat. It was pretty cool when it came out. Like when Amazon created DynamoDB in the 2000s, they put a paper out and said we're using consistent hashing, because there was an MIT paper from 99 or 2000 that talked about this in a project called Cord. And so a lot of these distributed databases, the NoSQL guys, the shared nothing systems that came out around 2010 or so, they're all using this technique. Actually, show of hands, who here has heard of consistent hashing before? Less than half. Okay. So the basic idea is that the key range is going to be a circle from 0 to 1. And the idea is that when I hash something, it's going to tell me where I'm going to land in the circle. And then I just move forward along the circle until I find the next node going in a clockwise fashion, or the next partition. And that's going to determine where the data I'm looking for can be found, or where the data I want to insert should be located. So say we have 3 partitions, P1, P2, P3. And then now I want to hash key 1. And I hash it, and then then just make it between the value range 0 and 1. So I'm going to land somewhere in the circle, and then now I know I just need to scan forward in clockwise fashion, and whatever partition I find along the ring of the circle at that point is where my data should be located. Same thing if I hash key 2 over here, I land at some point in the circle, and then I have to again scan up and try to find my next partition. So you sort of think the gap here between the 2 partitions along the circle, this corresponds to the data that they're responsible for. So P1 is responsible for everything going backwards up to P3. P3 is everything responsible going backwards to P2, and so forth. Right? All right, so how does this solve this partitioning thing that we talked about, or when I add a new partition? Well, say I add a new partition P4 down here, then I know that the only thing I need to move is the data that P3 was managing when I cut its part of the circle in half. And so all the data now from P4 to P2, that needs to get moved out of P3 and go now to P4. And everybody else on the circle doesn't get affected by this. Likewise, I add P5 up here, same thing. I split it and move the data around. And I keep doing it like this. So then the data structure you're going to use, I think they use a red-black tree or something. Like you need a data structure that everyone keeps coordinated to keep track of, like, here's what the current ring looks like, and here's the partitions that are available to you when you do these lookups. Yes?
So this method will not require each partition to evenly distribute on the circle.
The question is, in this example here, this does not require that the partitions are equally distributed, the data. Yeah, so the way you get around that one is that you have virtual partitions where you know that like multiple partitions around the ring will be assigned to a single node. And if you have enough of those, then assuming you're not terribly skewed, right? Assuming that your partition key isn't just the value 1, everyone has the same value, then you know things will be distributed enough for you. All right, so another thing that they can do, and we'll talk about replication in a second, is that I can now use the ring to help keep track of where data should be replicated to. So say I want to insert data into my database. When I first hash it, it's going to land it, tell me it goes into P1. But then I follow along the ring and say I want to replicate this 3 times. Right? So I want to have 3 copies of the data. Let's talk about how we handle that in a second. So I know that the primary location of the data should be in P1. But I'm also going to make a copy into P6 and P2 because they're now the next keys I see or the next partitions I see along the ring. And then now when I want to do a lookup, right, I look for, looking for key 1, it hashes, lands at this point in the ring, and I know I can either look at any of these 3 copies of the data of these different partitions to find the thing that I'm looking for. And we'll talk about how in sync these things are going to be. In the NoSQL world, when I do a write into P1, it's not going to immediately get propagated to P6 or P2. And then now I get into like inconsistent issues, which goes back to ACID stuff we were talking about a few more lectures. We'll cover that in a second. So as I said, Amazon uses this approach in DynamoDB, but then that was in the paper they put out. In the later follow-up paper they put out, 4 or 5 years ago, they announced they weren't using this, but consistent hashing is used in a lot of systems. Snowflake is going to use this to assign files to workers or data partitions to workers. Couchbase uses this internally. Cassandra uses this for distributing things across the key. React was a startup out of Boston that was a distributed key value store, and they went under 10 years ago. But you can see in the logo right here, you can kind of see you can see the ring, and then they have the fan out of the partitions being replicated along that ring. Right? So their logo was indicating they were using consistent hashing. So I think consistent hashing was invented at MIT in 97, 98. But a year before that, there was another paper came out on a technique called rendezvous hashing. And I think the theory shows that the consistent hashing is a specialized subset of rendezvous hashing. The basic idea here is that for every single key we want to hash, or we want to assign to a partition in our database, we're going to generate multiple hashes for it, where for each hash we're going to append like the partition ID or the node identifier of the different nodes we have in our cluster, and then we're going to choose assign the key to a partition for the one that has the highest hash value. So say again, here's our data. We want to use this column here as the partition key. So what we're going to do is we take the key here, and we're going to hash it, but we're going to concatenate the key value, in this case A, along with some representation of the node or the partition identifier. Right? Like think of just like you're literally just smashing the bytes together, and then you're hashing it, and then you're going to get a bunch of hash values come out of that. And then now what you're going to do for all the other keys, you're just going to choose whatever the hash value that has as the highest one, and that tells you what node, what partition the key should be assigned to. And so now if I add a new key, I just do the same thing, right? And I end up with a ranked order like this, and that determines where it goes. And then again, the problem we're trying to solve is if I add or remove partitions or nodes in my system, I don't want to have to remove everything around. So the way that basically works, if I add another node, then I just do all the hashing again, and it may be the case that some of the data will get moved, but some of the data will still be the same because it's going to be based on the ranking of the hash values when I run this. So in the case here of D, going back here, before I added node 4, it was unassigned node 2, but when I hash D with node 4, it turns out node 4 is the highest ranked hash value. So then I only have to move key D to that new partition. So this is going to be faster lookups because it's log n to go find the data you want, whereas in consistent hashing, I think it's log n. Sorry, it's on, whereas this is log n. Okay. So the next thing we need to talk about is how we're going to make multiple copies of data, and either at the entire tables, the individual records or files, it doesn't matter what it is. How we're going to make copies of that data and put it across multiple nodes so that, again, if one of those nodes crashes, we don't have to stop the world. We don't have to take the whole system down waiting for that node to recover. We can keep up and running. So most data systems in the world that are distributed databases, meaning running on one or more machine or two or more machines, are going to be doing basic replication. So it'll still be a shared everything box running on a single node, but then they'll do replication to propagate the changes on that one node to another node or multiple nodes, so that if the main node, the primary node goes down, I can just recover, promote the replicas to become the new primary. So everything we're talking here is still going to will be applicable to whether you're doing partition databases or non-partition databases, whether it's share nothing or share disk, right? You still want to do all these things. So the first question is, what's the configuration of this replication scheme going to look like? How we're going to then propagate changes from one node to another node? When should those changes get applied? And how are transactions or queries updating that data, and then for them to determine how to propagate those changes? So let me go through each of these, right? So the first question is, again, for any piece of data, who is responsible for it, and where could multiple copies of that piece of data exist? And so primary replica is the most common one, where for any single object in our database, there'll be some node or partition is now considered the primary location of it. Again, whether it's on shared disk or shared nothing, it doesn't matter. It knows that any write or any modification I want to make to that object has to go to that primary node. And then that primary node is responsible for propagating those changes to that object to any replica that's following along behind it. And then if and when the primary goes down, then we run what's called leader election, where we determine what's going to be the new primary for any object. And this basically looks like a transaction as we had before. Think of, we have a table that says for any node, any object, here's the primary node responsible for it. So I just run a transaction on that, decide how to update that atomically, decide to promote a new primary. And then this is where Paxos and Raft come in to do that kind of thing, or two-phase commit. Another choice, it's less common, is to do multi-primary, where this is an object can exist at any location in our distributed system, and therefore it can be updated by any one of these nodes. And then I got to resolve any conflicts I have if two nodes update the same object. How do I decide which of these, which should be the latest version that successfully commit? So like I said, primary replica is the most common one, right? People are running, Postgres in enterprise settings. Most Postgres instances are running on a single box, and they'll be doing something like this. So all the reads and writes can go to the primary, and then when transactions commit or as changes are being applied, the updates get propagated to the replicas, right? And in some systems, you can actually then run read-only queries on the replicas, right? If you know your queries aren't going to update any data, you can hand them off to the read replicas, and that way you don't interfere with anything on the primary. So you want the writes to go as fast as possible, so you want to offload them from the primary if you can. But again, depending on how you're propagating updates, we'll talk about in a second, the reads on the replicas might be reading stale data. And again, for some applications, that might be okay. What's less common is to do multi-primary, and this is where reads and writes can go to any node on any object. And then now the nodes are responsible for communicating and coordinating with each other, or through a centralized coordinator to determine which writes should succeed and which writes should not succeed. And if one thing gets written at the bottom, you know that it wants to get propagated to the top, or likewise the other way. Yes. Yes. The question is, I said in primary replica, you want to do leader election. Why would you ever want to change what the primary is? This node catches on fire, goes down, crashes. Which one is now the new primary? Right? And then now you got, say, this node goes down, the two replicas say they're both going to be the primary. Well, you only want one of them to win, so you need leader election for that. Yes? The question is, in a multi-primary, what's an example where you would want one write to succeed on one node and not the other? Say you're trying to guarantee the ordering of transactions serializable, and you and I write to the same thing at the same time. Only one of them should succeed. Or say we write to two things at the same time. You write two things, I write two things. So I should see all my writes or all your writes, and not a mix of the two. So one of those transactions has to fail. And that's going to be the two-phase locking or OCC, all the stuff we talked about before. Yes? The question is, should you use something like multi-paxos? Yes, next class. Right? What's that? The question is, where, if I'm doing 2PL, where do I store the locks? A few more slides. All right, so let me switch case safety. Let's talk about the propagation scheme, and then I'll get to your question. All right. Case safety says basically how many replicas do I have to have in order to stay up. So if I have 3 copies of the data, and my case safety factor is 1, meaning like I need to have at least 1 copy of the data live. So if 2 nodes go down, rather than me still taking updates to update the database, I say, I'm not in a safe mode right now. I'm going to stop the system. Don't take any new updates because I don't want to make changes to my node and then have that node go down and end up losing them. So you can specify how many machines need to be up or how many copies of data you need to have in order for the system to stay online. All right, so if we update data on a node, whether it's multi-primary or primary replica, and again, in a multi-primary world, you still can have replicas. Right? Every primary can have its own bunch of replicas that keeps in sync as well. They're not mutually exclusive. But now the question is, if I update something on the primary, should I wait until the replicas acknowledge that they got those rights before I tell the outside world that your transaction has succeeded or your update has succeeded? So if you're going to wait, this is called synchronous, synchronous propagation or and strong consistency. And the idea is that my transaction did a bunch of updates on this node here. That's the primary. And it has a replica behind it. I'm going to propagate those changes to the replica. I'm going to tell it to flush. And I have to wait until the replica comes back and says, yes, I got your changes. And they're durable on disk. I flushed them on disk. And so the primary has to wait. And then once it finishes, it sends the acknowledgement and says, the thing you asked me to write to disk, I wrote to disk successfully. And then and only then do you tell the outside world your transaction is committed. And if you have multiple replicas in different locations, they all, if you want things to be very strong consistency, they all have to agree that this transaction is committing. We'll talk about how we're going to do that next class. Before you tell the outside world you committed. And that way, if the primary goes down, or that the changes have been applied to the replica. Yes. Question is this two-phase commit? Two-phase commit is one way to do this, yes. The key idea is, though, I'm waiting for everyone to come back and say, yep, I got what you wanted, and before you tell the outside world you committed. Asynchronous would be, the outside world tells me I want to commit. I can send a message to the replica and say, hey, I got this change. Go ahead and commit the change for me. But I'm not going to wait for it to come back. I'm going to immediately tell you, say, yep, I got your change. Right? And then eventually this thing will flush. Of course, now there's a brief window where, like, if this thing crashes and maybe this thing crashes, but I've already told you your transaction committed, then I come back and it's gone. Right? Because maybe I wrote to the log on this guy here, right? And it's a shared nothing system. The log is on the local box, but that node gets nuked. The log is gone. And now your change didn't actually get propagated to everyone else, and you go try to read it and it's not there anymore. So the NoSQL guys were all about this thing because they said, oh, we don't want to wait for transactions to commit. They didn't even have really notion of transactions. Whereas if you care about, really care about not losing data, you want to do the thing at the top. You can play games about things like, I'm showing only one primary and one replica. You could say, well, I have one primary and 3 replicas. And as long as 2 of my replicas come back and say they got my change, then I'm not going to wait for the 3rd one. Right? You could do that and try to reduce the amount of time you have to wait. So, okay. Propagation timing just basically says when you actually send going back here, when you actually send the changes from the primary to the replica. So you could do this continuously. So every single time you do an update in the middle of a transaction, you propagate that change to the other node. And then that way when you go to commit, it's basically applied all the changes and just sending the commit message. Or if you do it upon commit, you basically stage all the updates on the primary, and then only when you get commit message from the application, then you send all the updates you want to have to apply to the replicas along with the commit message. You have to wait longer for them to apply the changes and come back to you. But the idea here is that you don't have to ask them to abort and roll anything back. Most systems do the top one and not the bottom one. All right, so I'll come back next class and I'll talk about active-active versus active-passive. But I want to talk about a bunch of these things that have been coming up, like, okay, well, what's the architecture of the distributed system? Who's talking to what? Is there something in the, is there a centralized piece that can coordinate everything that we want to do? And then this will segue into distributed current control next class. So if all our transactions need to update only data on a single box, that's easy to do, right? Every box can just run its own, local current control. It doesn't need to coordinate with anybody else, right? Ignoring replica stuff. It just applies all its changes and commits and done. It's when I have to start touching data across multiple nodes, especially if I have replicas, and I want to make sure that those guys are all agreeing that we're committing transactions together, then I need a mechanism to coordinate all of that, right? And there's two approaches. One is to use a centralized coordinator. Think of this like a global traffic cop that has a complete understanding of all the transactions that are running in my system at any given time. And it's where I can store my locks if I want to in that centralized location. Or it can be completely decentralized and have the nodes themselves decide how they're going to choose when to commit. Now, you still can do a leader election in a decentralized architecture because one node has to say, this is what we want to do. But there isn't going to be a complete global view of all the transactions running in the system. So in a centralized architecture, you have this sort of coordinator sitting on the side. And say my transaction wants to show up and wants to touch data in these three partitions. So I'm first going to send my lock request for the data I want to access. And this can be either done because I'm sending the query, and this thing knows how to parse that query and break it up. Or you can say explicitly, I want to lock data at these partitions within these ranges or these values or something, right? There's some lock request to a coordinator up above. And then now this is maintaining this lock information, sends back the acknowledgement to the application that you got this, you acquired these locks that you wanted. And then now the application can send whatever queries it wants to the partitions to do whatever it needed. And then now when it wants to go to commit, it has to go to the coordinator and says, hey, I want to commit my transaction. Here's what I did. The coordinator is then responsible for communicating with the other partitions and say, hey, this transaction made some changes on you. Is it safe to commit this? Again, they're all running their own local concurrency protocol to decide what's allowed to commit or not. And then if they send back the acknowledgement that that this transaction is allowed to commit, then only then the coordinator can send back the response to the application that said you're allowed to commit. This is how people built distributed databases back in the 80s or 90s. There was a bunch of products, they're called, in the old days they were called TP monitor, or they still are called TP monitors, but it stood for, in the old days it stood for telecom processing monitor, and then over time the acronym just got changed to be transaction processing monitor. But it's basically a centralized coordinator that knows how to run distributed transactions across multiple nodes. And then there was in the 90s, there was an effort to standardize the protocol in which you can have a TP monitor communicate with the different partitions. This thing's called OpenXA or something. Yeah, OpenXA. It was like a transaction protocol that says basically do 2PL coordination across different devices or different systems. So you could have your TP monitor, the coordinator at the top, communicate with an Oracle database and a times10 database or a nonstop SQL database, and knew how to do distributed transactions across them. And everyone was still running their own local thing. BEA was another famous one that got bought by Oracle. I know the founder of BEA. The dude's amazing. He's hilarious. He wrote one of the first database systems on Solaris in the 1980s at Sun. Transarc was founded by, actually came out of the Andrew file system project here at CMU, the Andrew project, right? And this was founded by Jeff Eppinger in the software engineering department and got bought by IBM. I don't think it's still around. And then OMID is a TP monitor for running transactions on HBase and other systems. This is not that common. What is more common is using a middleware approach. It's basically the same thing, It's just now all the queries go to this centralized thing directly, and this is responsible for routing all the queries and maintaining the lock table and sending all the requests to the different nodes as needed. So it looks like a single database server instance into the application server, but behind the scenes, it's coordinating across this different nodes, right? This is what Google did back in the day when they started out MySQL before Spanner. They basically did the same thing. This is also what Facebook does still today, right? Facebook runs the largest MySQL cluster, and it's basically using a middleware approach to look like a single logical database. All right, last slide. Decentralized coordinator. Basically, the idea is that you can start a transaction request to any node. Somehow there's a leader election to decide that this node is going to be responsible for coordinating everything. The application can then send requests either to individual nodes or even to the leader and let the leader route things for you. But when it comes time to commit, the leader is responsible for interacting with the other partitions that are involved in this transaction and saying, is this transaction allowed to commit, yes or no? And we'll talk about next class how we're actually going to run this. All right, so I'm going to skip federated databases next class. Basically, it's the middleware approach, but like the idea is that instead of having all the nodes on you're talking to be the same database system, like it's MySQL, just different copies of it or different instances running different nodes, I can have in a federated database, I can have a single view into through this middleware that then knows how to take a single query and send the request to whatever database server you want to connect this to. So it looks like your Mongo database, your MySQL database, your Postgres database all looks like a single database system, but this middleware is hiding all that from you. These are not that common. They don't work very well, but this is an idea that's been around for a while, and this goes back to the 1990s. All right, so let me just quickly talk about this, and this will take us to the next class. So say now I want to run a transaction that wants to talk data across two different nodes or different partitions. Things are easy if they're only touching one thing at a time, but as soon as I have to start touching data that is at different nodes, then this becomes problematic because now we have to do either two-phase locking or OCC, whatever we talked about before, and now I have to worry about deadlocks and all the things we talked about on a single node. I got to make this work in a distributed environment. And if they're in the same rack, then yeah, communication will be kind of fast, but if I'm running across the wide area network, across wide geographical regions like US East, US West in AWS, then this is hard. So that's what we'll come off next class. We'll talk about how we actually, how we do distributed OLTP systems and distributed OLAP systems to do joins across different nodes. But everything we talk about today is the foundation of building an initial distributed data system. Okay? Any questions? In the back, yes. Say it again. Is there any existing implementation of a federated database? So Trino or Presto will kind of give you this now with using connectors. Postgres farm data wrappers are essentially kind of doing the same thing now too, right? The problem is what you want to do is the idea is a query shows up, and then whatever the middleware system, they would know, oh, you want to touch data at this database system, and knows how to then carve off whatever the part of the query that needs to run in that system and try to push down predicates, projections, try to send down a query request that's specialized to that, whatever the target data system to do. Oftentimes they can't do that, and it's usually like a select star query to suck all the data up. So that's the big challenge there, right? Because you end up building the lowest common denominator for a wide variety of systems you would support. Okay? In the back, yes? Question, aren't parallel databases essentially the same as shared disk databases? Yes. And you could argue also too that like a parallel database where you're attached to like a NAS or a storage attack network, like is that the same thing? Sort of, yes, but like we'll see next class, you can actually have different architectures where like the write-ahead log gets distributed to the shared disk, and you still then coordinate across them. It's slightly different, but at a high level, yes. Like if I have a single box that has like 20 CPU sockets in it, is that the same thing as a distributed database? At a high level, yes. But some architecture decisions you make it be different. Okay, all right, guys. Have a good holiday. See you on Monday next week.
Get the fortune.
maintain, but never strain flow with the grain.